Good afternoon, everyone, and thanks for listening to this presentation. Here, I will be describing some of the theory and experiments behind the paper titled Articulatory Gesture-Rich Representation Learning of Phonological Units in Low-Resource Settings. The problem statement that we are tackling in this paper is twofold. First is to learn representation of speech signal which is capable of stripping off extra linguistic information out of speech signal. As we know, speech is highly expressive and contains some paralinguistic information such as speaker and emotional content. We want to create a representation which contains only linguistic information. More specifically, just the articulatory gesture-rich information. Second problem is to create a phonetic inventory, discover these phonetic units, and automatically create this inventory from untranscribed speech data. The main motivation behind this paper is to be able to process enormous amount of conversational speech data that is being generated in multiple languages. And in case of Indian scenario, the languages can be code mixed. We experiment with unsupervised techniques because we want to alleviate the need for manual labor which is invested in transcribing speech data. Blumstein and Stevens hypothesized that humans perceive the speech sounds by their gross characteristics. Brauman and Goldstein proposed articulatory phonology as a field to unite phonetics and phonology. This gives us inspiration to learn articulatory gestures as the fundamental units of speech. There have been further studies by Ostendorf, Arity and McKenna, Tomer, which use extra information such as manifold learning techniques and acoustically and linguistically derived features instead of conventional phoneme-based speech recognition where a beats on the string model is followed. According to our proposed method, an optional feature extraction is done over raw speech signal, and then these features are subjected to several low dimension manifold learning techniques. These manifold learning techniques are constrained by gestural relevance. Each of these representations are subjected to evaluation for two tasks: phoneme classification and ABX discriminability measure, which is proposed by Zero Resource Speech Challenge. Further, these representations are clustered using Dirichlet process Gaussian mixture model, which is a non-parametric method to find clusters in raw data. We also experiment with the concentration parameter of DPGMM in order to obtain different set of clusters and fix the parameter as we obtain the representations which correspond to a manner of articulation classes. Our proposed technique is able to learn manner of articulation classes in an unsupervised manner from a lot of raw speech data. This speech data is windowed in short time and subjected to different manifold learning algorithms. We also obtain the inventory not just from a single language but from a mixture of several languages. Our further studies show that these features can be robustly used for the task of keyword spotting. Now let us look at the models that we have used for learning these representations. First, we explain autoencoders, which are also called auto-associative neural networks. These are deep neural networks which take input and output as some data sample point and minimize the reconstruction error. We use a special form of autoencoders which are called correspondence autoencoders. In such architectures, input tries to learn to reconstruct a different sample from the same class. This forces the network to learn class-specific properties inside the data. Autoencoders have several advantages over manifold learning techniques. One of those is that the weights are optimized iteratively rather than in a single manner, where manifold learning techniques use a lot of computation and memory. Autoencoders also build abstraction of features by reusing the features obtained in the previous layers. We also experiment with convolutional autoencoders. These are the special form of autoencoders where a dense layer is preceded by convolutional and max pooling layer, and further followed by upsampling and deconvolution layer for reconstruction. This form of deep neural network is highly parallelizable because of independent processing of convolutional feature maps, and also builds robustness against noise by max pooling mechanism. In order to create an exhaustive comparative study, we experiment with several manifold learning algorithms. Manifold learning algorithms basically project a high dimension space into a low dimension space by obtaining maximizing the data density. A rough flowchart of manifold learning would look like creation of sample-wise similarity measure and then obtaining a nearest neighbor graph. This graph is traversed to find the nodes which are nearer by writing a cost function. We experiment using three different set of manifold learning algorithms, namely locally linear embedding, isometric mapping, and Laplacian eigenmaps. The data that we used for our experiments is a conversational speech data, that is Buckeye corpus, which has 40 speakers and 42 phoneme classes. We extract 500 samples of each phoneme class and window it at 25 millisecond and overlap of 10 millisecond to create the frames. These phoneme classes are further clustered into broad manner of articulation categories. These broad manner of articulation categories are used to obtain the correspondence pair using which we learned the autoencoders. We experiment with different architecture of convolution autoencoders, but we obtain a result which is performing best in case when we use 16 feature maps followed by 32 feature maps, each of size 1 by 3, and a max pooling of 1 by 2. The weights are optimized using Adam learning algorithm. We evaluate each of the representation using two methods. First is phoneme classification using support vector machines, and second is ABX discriminability test, which is proposed by zero resource speech challenge. These are some of the results that we obtained using SVM for phone classification task. As you can see, most of the manifold learning techniques do not perform very well and they are inferior to MFCCs, but isometric mapping outperform MFCCs. both the types of standard autoencoders and convolution autoencoders outperform MFCCs by a large margin, even in very low dimensions. We also create some visualizations to see the embeddings obtained by various methods in 2 dimensions. As we can see that local linear embedding do not separate the 3 phoneme classes very well, but isometric mapping and convolutional autoencoders are able to separate and create well-defined boundaries around the 3 phoneme classes. Another qualitative measure that we obtained was to see the 10-dimension representation of convolutional autoencoders. We can see that the 2 vowel MFCCs are very different visually, but the representation obtained using convolutional autoencoders in 10 dimension are almost identical. We also apply convolutional autoencoders and isomap over Buckeye corpus and Zitsonga corpus given as a part of zero resource speech challenge. We can see that both of these algorithms outperform the baseline, but they perform comparably equal to each other. We then further apply Dirichlet process Gaussian mixture models to obtain the discrete phonetic inventory in order to get the representations which can be clustered based on the manner of articulation. Here we have on the x-axis the phoneme classes, and on the y-axis we have the clusters obtained using DPGMM. We can see that MFCCs do not well cluster across different manner of articulation, whereas convolutional autoencoders are able to form small clusters which correspond and cluster based on the manner of articulation classes. So, to summarize the paper, we have investigated a lot of manifold learning algorithms to discover these fundamental phonetic units in speech data. We have seen that convolutional autoencoders prove to be the best in terms of computation as well as accuracy, and the representations obtained using conv-A are highly separable. As the future work, we would like to experiment with recurrent autoencoders, which can capture the temporal dependencies between the sample in articulatory gesture unit. Thank you for listening to the presentation. Please send me any queries or questions that you have regarding this presentation on the email address displayed on the screen. Thank you so much.